This video is about Isaac Physics 42, which is refraction, 48, which is convex lenses, and 49, which is concave lenses. Refraction happens with all sorts of waves, but it is easier to visualize with light. On a diagram such as this, a ray indicates the direction that the energy is being transmitted, here. Refraction is the phenomena where the ray changes direction as it changes speed. On this diagram, we have drawn two media, labelled medium 1 at the top, medium 2 at the bottom. And the ray of light is incident on the boundary between those two media. On the diagram, I've indicated the angle of incidence with an I, and it is measured to the normal. The normal is an imaginary line 90 degrees to the boundary surface, and I've indicated that with this dotted line. If medium 2 is more optically dense than medium 1, then the ray will refract towards the normal, which means the ray diagram would show a ray in this direction here. You can see that the angle of refraction, which I've labelled here with an R, measured to the normal, is smaller than the angle of incidence, indicating that the ray has changed direction, it has been bent, so that it is going towards the normal. If, however, medium 1 is more optically dense than medium 2, so medium 2 is less optically dense than medium 1, in that case, the ray will be refracted away from the normal. Here you can see the angle of refraction is now bigger than the angle of incidence. And the angle of incidence and the angle of refraction are always measured to the normal. Now, I've used the phrase optically dense. What does that mean? Well, optically dense refers to a property that materials have where they slow light down. And the more optically dense a medium is, the more it slows light down. You may recall that density is mass divided by volume, but that's unrelated to optical density. Water is more physically dense than paraffin, but paraffin is more optically dense than water. Glass, on the other hand, is more physically dense and more optically dense than water. So optical density and physical density aren't related to each other. But the more optically dense a medium is, the slower light will go through it. Light can't travel faster than it does through a vacuum. The speed of light I've given here to three significant figures as 300 million meters per second. You can quantify optical density using a quantity called refractive index. Now, refractive index is no longer included on the GCSE specifications, but I'm talking about it here because it makes the subject of refraction clearer. A medium with a higher refractive index has a higher optical density, and vice versa. Now here I've got the speed of light within some medium. We don't know what that is. Perhaps it's glass, and the speed of light in glass is about 200 million meters per second. But over here we've got the speed of light in a vacuum, which I've labelled C0, 300 million meters per second. The refractive index of some medium, which we use the letter N for this, so N for some medium, is equal to the speed of light in a vacuum divided by the speed of light in that medium. So with our glass example, the speed of light in glass was 200 million meters per second. 300 million meters per second divided by 200 million meters per second is 1.5. So the refractive index of glass is about 1.5. Refractive indices are always greater than or equal to 1. And that's because the speed of light in a medium will always be less than or equal to the speed of light in a vacuum. A bigger refractive index means a more optically dense medium, and therefore the light will travel slower through it. So if we wish to determine whether light refracts towards or away from the normal, we need to look at the refractive indices of the two media and compare those refractive indices. So here I've given two examples in these diagrams. On the left, you'll see the situation where light is traveling from a medium which is more optically dense into a medium that is less optically dense. In both of these examples, I've used medium 1 as the medium from which the light is travelling, and medium 2 as the medium into which the light is travelling. So I, the angle of incidence, is always that angle in medium 1, and R, the angle of refraction, is always that angle in medium 2. You can see on the diagram on the left that the light is travelling from a more dense to a less dense medium. That means that the light goes faster in medium 2 than it does in medium 1. That means the angle of refraction has to be greater than the angle of incidence. And that is why this ray is refracted away from the normal. The diagram on the right, we can see that the ray is now entering a medium which is more optically dense, n equals 1.7 for medium 2, but it's only 1.5 for medium 1. In that case, the ray of light is refracted towards the normal, because the speed of light in medium 1 is going to be greater than the speed of light in medium 2. Medium 2 slows the light down. You can see from these two examples that you can cut out refractive index altogether and just compare the speeds of light in those two media. In whichever medium the light goes faster, the angle will be greater. Well, that's refraction. Let's move on to convex lenses. A convex lens is one which is thicker in the middle and thinner at the edges. All lenses have focal lengths, and I've indicated the focal point, which is one focal length away from the center of the lens, with these two x's, and labeled them F. This line going through the center of the lens, horizontally in this case, is the principal axis. And this is the axis of symmetry for the lens going vertically. In this example, we are going to place an object indicated with this arrow here, somewhere to the left of the lens, and consider light emerging from the top of this object. Now, light will emerge from the top of this object in all directions if it's scattering light from some other source, or if it's a light source of its own. It will scatter light in all directions. So we're going to consider just two principal rays to identify the position of the image. There are three principal rays, but you only need to be able to use two of them in your GCSE, and two is sufficient to identify the position of the image produced when you view this object through this lens. I mentioned before that the focal point is placed one focal length away from the lens. The focal point is a point through which rays will converge if they are parallel when entering the lens. So parallel rays entering this lens will be refracted so that they converge and cross at this point here, the focal point. And parallel rays traveling from the right-hand side into the lens will converge, they will refract and converge on this point here. Well, let's draw the two principal rays, and then we'll move the object and redraw them, and you'll see how straightforward these diagrams can be. The first principal ray starts at the top of the object, is parallel to the principal axis, and then gets refracted through the far focal point. Take extra care when drawing your diagram, because the more accurately you draw it, the more accurately you'll be able to determine the position of your image. You will notice that this principal ray passes through the lens until it reaches this line of symmetry and then is refracted. This works for very thin lenses. For thicker lenses, the physics gets quite a bit more complicated, but for thin lenses, this is fine. The second principal ray passes straight through the center of the lens, undeflected. Again, take extra care when drawing the rays to make sure that you're happy with where they are. Use a ruler. And you'll see the two rays cross at this point here. This point here is where the image forms from the light that passes from the top of the object through the lens. The image is the point from which it appears as though the rays are diverging. If I was stood over here, looking along these rays, then this is the point from which I would think the rays are diverging. I wouldn't necessarily know that there's a lens here and an object all the way back here. So this point here is the image, the point from where rays appear to diverge. Now I could do exactly the same thing, drawing the same two principal rays from any point on this object. And if I did that, I'd discover that the image is vertically orientated, just like the object is. And the bottom of the object forms an image which is very close to the principal axis as well. In fact, the point on the principal axis forms an image on the principal axis. And this means that I don't have to draw all of those rays. I really can get away with just drawing two rays to locate the position of the image. Our image is drawn here. And you will notice it is smaller than the object. The word we use for that is diminished. The light does in fact cross that point, so we call it a real image. And because it is upside down, we can call it an inverted image. So this is a diminished real inverted image, or a real diminished inverted image. I don't think it matters what order you put these words in. And those are the two principal rays. So we could draw them from the object, wherever we place the object. Let's place the object here and see where the principal rays put our image. Our first principal ray is from the top of the object, parallel to the principal axis, and then is deflected through the focal point. Our second principal ray is through the center of the lens undeflected. You'll see the image is going to form somewhere, some distance away from the lens. And if I take extra care when drawing my diagram, making sure everything lines up properly, I can see that the image will form all the way down here. This image is still real because the rays of light do in fact cross at that position. It is now larger. We can either say it's an augmented image or just a magnified image. And it's still inverted. It's still the wrong way up. The magnification of a lens will be the size of the image, and I'll use a capital I to indicate that, divided by the size of the object. I'll use a capital O to indicate that. So if the magnification equals 1, the image is the same size as the object. If the magnification equals 2, the image is twice the size of the object. If the magnification is 0.5, the image is half the size of the object. Now, the only tricky thing with convex lenses is what happens when the object is closer to the lens than one focal length. We'll follow the same rules as we had last time. We will draw our first principal ray parallel to the principal axis, then refracted through the focal point on the other side of the lens. We will draw our second principal ray from the top of the object straight through the center of the lens, undeflected. And you'll notice the rays are now diverging. They're not traveling towards each other as they were before. They're now traveling away from each other. But remember, our image is the point from which it appears as though the rays are diverging. And that means it appears as though the rays are diverging from some point back here. If I extend those lines back to where they appear to cross, that will indicate to me the position of the image. I've used dotted lines when I've projected these rays back because I want to make it clear that these are virtual rays. The light does not actually cross at this position. It just appears to us as though that's the point from where the light rays are diverging. So that is not a real image. That's a virtual image. It's a virtual image because the light rays do not actually cross there. It just appears as though they diverge from that point. It is larger than the object, so we could say it is augmented or magnified. And we can use the same equation as last time, where we can say the image size divided by the object size is the magnification. Although technically, because the image and the object are the same way up, this would actually be negative magnification. But without going into the thin lens equation, we don't really need to know why that is at the moment. Now, the word we use to describe an image that's the same way up as the object is either upright or erect. So this image is virtual, augmented, and upright. The other type of lens is a concave lens. Concave lenses are thinner in the middle than they are at the edges. The principal rays for concave lenses are slightly different. with the first principal ray, rather than being refracted towards the far focal point, it is refracted away from the near focal point, like that. But of course I'm using a dotted line here because the ray does not actually pass through this place. It just appears as though the ray originated from along this line. Somewhere along this line is where our eye thinks the ray originated. It actually came from over here. The second principal ray passes through the center of the lens undeflected, just like it did for convex lenses. And just as before, the point from which those two rays appear to diverge is our image. You can see that point is here. This is a virtual image because the light from this first principal ray doesn't actually cross through this point. It's not a real image. It's a virtual image. It is diminished compared to the size of the object, but it is upright. You could place this object anywhere along this principal axis and use the same two principal rays to determine the position of the image. And you can measure the magnification of the lens by doing the image height divided by the object height, just as you did before. My top tip with all of these is to make sure you draw diagrams to help you out, especially for lenses. The more accurately you draw your diagram, the better your results will be.